Impedance response. What's that? Why do we need it? What's it good for? That's what I'm going to explain today. Hi there, this is Marius Laubeker from Hamburg, Germany. And welcome to the Laubeker podcast number 2. Our today's topic is impedance response. I also call it impedance plot. The German version is linked in the comments below. First of all, the impedance plot is a Bode plot. The x-axis is scaled logarithmically as in a frequency response plot. All decades have the same width. That means that 10 to 100 Hz is, for example, as wide as 100 to 1000 Hz. Basically, it depicts the resistance of a speaker at every single frequency, because speakers are a complex system. They contain a system similar to a mass connected to a spring, which causes the peak at the resonance frequency. The pole piece enlarges the inductance of the voice coil, which causes the rising ramp to high frequencies. Other resonances within the driver can also cause peaks in the plot. Even a normal resistor does not have a linear plot because, firstly, if they are made from a wound wire, they have a small inductance, and secondly, in any wire, the proximity effect increases towards higher frequencies. At high frequencies, electrons tend to move only on the surface of a conductor, and therefore the resistance, the real part of the impedance, increases. That, of course, is also the case on a wound wire. It can be prevented by using multi-strand wires, which have a bigger surface than solid wires of the equivalent cross-sectional area. But inside a resistor you usually have solid wires. Thus, the proximity effect can be observed from about 1 kHz on. The impedance response reveals much information about the driver and even more about a complete speaker. Mainly the region between 0 and 20, or let's say 25 ohms, is most interesting. If you look only at that range, you have a higher resolution and are able to recognize resonances better, or whatever interesting is there to see. It is, for example, easier to determine the nominal impedance of a complete speaker, which is the lowest value in the whole range of 20 Hz to 20 kHz. A German industrial standard defines that the minimum may be 20% less than the nominal value, which means, for example, 3.2 ohms for a 4 ohm speaker. If the value is less than 3.2 ohms, it has to be called 3 or 2 ohms, depending on how low the value exactly is. The top of the peak at the resonant frequency may be located outside of the diagram because it is only necessary to know the exact point and value for TSP calculation. But that'll be another podcast. Usually it is more interesting to have more resolution to be able to see other things more clearly. Smaller peaks in other parts of the plot may indicate further resonances. To find out exactly, you have to look at the distortion plot and the waterfall diagram and see if there are also resonances visible at the same frequencies. Especially if they are visible on all 3 plots, they might be audible. If they are not visible on all of them, you can't be sure, but you know what to look for in a listening test. The impedance plot of a whole speaker tells you something about the enclosure type, number of ways, and the crossover network. You can see if the crossover network contains series or parallel RLC circuits. Series RLC circuits in parallel to the driver usually cause a dip in the plot, and parallel RLC circuits in series to the driver cause a peak. Parallel RLC circuits in series to the driver are mostly found in full-range speakers, another topic for a future podcast. In multi-way speakers, peaks are normally near crossover frequencies. A closed box has one peak in the base. A high-pass filtered closed box has a ramp below that towards the low base because the capacitor in series has a high impedance at low frequencies. A bass reflex box has a double peak with a minimum in between at the tuning frequency of the port. At the crossover frequencies there is usually also a high peak. A horn speaker has many peaks in the bass, which sometimes are very close to or overlap each other. That is due to the fact that horns amplify several frequencies and also constellations appear. A transmission line cannot clearly be determined by looking at the impedance plot. There might be only one or even two peaks. That varies depending on the design of the line. I looked at several projects in the German DIY magazine Hobby Hi-Fi, and their impedance responses look really different to each other. Another reason for that is that Hobby Hi-Fi often uses internal Helmholtz absorber chambers to suppress particular resonances, which therefore might not appear on the impedance plot. A leaky closed box can also be recognized. This is basically a bass reflex box where the port is filled with an absorber material. You use this for drivers with a high QTS, mostly bigger than 1, that do not work well in either bass reflex or closed boxes. In a closed box, their frequency response has a high peak in the bass, and the well-defined leak in comparison attenuates that peak a bit. The impedance block looks similar to a normal closed box, with the difference that the impedance peak at the resonant frequency is asymmetrical. The lower slope of that peak is not as steep as the higher slope. It looks more like a sawtooth. I'm planning on making podcasts about enclosure types, and then I'll also tell something about leaky closed boxes. You can also determine how big the output impedance, respectively the damping factor of the amplifier, needs to be from looking at the impedance response of a speaker. If the speaker has a big range in impedance, the output impedance of the amp needs to be small. That means the damping factor has to be big. Valve amps, for example, have the disadvantage of high output impedances, which may be even 3, 4 or 5 ohms. That forms a voltage divider with the speaker, which causes a deformation of the frequency response of the whole system. The more the impedance varies, the more the frequency response gets deformed. The impedance response is also probably important in combination with Class D amplifiers, aka digital amps. Tests of those in Hobby Hi-Fi showed that some have the same effect at high frequencies. This is caused by the low-pass filter, which is installed in their speaker terminals to filter out the carrier frequency. The cutoff frequency of this low pass is determined by the impedance of the speaker and can cause an amplification at high impedance or an attenuation at a low impedance. How much depends on the inductance of the coil. It might be up to 2 or 3 decibels. Another thing you can see in impedance responses of bass reflex boxes is the Q factor of the enclosure. In Hobby Hi-Fi issue 4 2004, for example, you find an article about how to calculate this from measuring the height of the minimum between the two peaks in the bass in comparison to the DC resistance. Basically, this shows how leaky the box is, and especially in a bass reflex box you want the acoustical energy to leave only through the port and not lose it through gaps or deformation of walls. Furthermore, with the help of an impedance response, you can measure capacitance and inductance values of crossover parts. By measuring the impedance curve of capacitors, coils and resistors in the software LIMP, which I use, you can calculate resistance and capacitance or inductance by one click at any frequency where you place the cursor on the plot. That works because LIMP also measures the phase of the impedance. Impedance, in equations represented by letter Z, not only consists of the argument of Z, which is shown in the impedance response, but also of the phase difference between voltage and current. Okay, buckle up. Now we take a short detour through the kingdom of complex numbers and the complex calculation of alternating current. You can depict impedance as polar coordinates for one frequency. The argument of Z from the impedance plot is the length of the pointer at the particular frequency in polar coordinates, and the angle between the pointer and the positive x-axis is the phase. You could also calculate Cartesian coordinates from that. The x value is the real part of the impedance and the y value the imaginary part. For an ideal resistor, the real part is exactly the resistance and the imaginary part should be 0. For ideal capacitors and inductors, the real part is 0 and the angle is plus or minus 90 degrees. In German we have two nice mnemonics. Im Kondensator eilt Strom vor, something like in a capacitor the current hurries to be the first, and in Induktivitäten die Ströme sich verspäten, which means in inductors the currents are late. I also found an English mnemonic for that, Eli the Iceman. E stands for voltage, I for current, L is an inductor and C a capacitor. Now Eli, E-L-I, means E leads I in an L. That is, voltage leads current in an inductor, and ice means I leads E in a C. That means current leads voltage in a capacitor. This shows the shift between voltage and current. Basically, this is a bit too complicated to describe it only with words. It might be a topic for a video. On the other hand, there's the possibility to look it up at Wikipedia. There might be a descriptive sketch to understand it better. That's all for today. Next planned topics are crossover networks, distortion plot, waterfall spectrum, Thiele small parameters, and various enclosure types. If you have other suggestions, please write a comment below. If you found a mistake, please have a look at the comments to see if I already corrected it. If I didn't, then leave a message. Thank you for listening, and I'm happy if you listen to my other podcasts or watch some of my videos. If you like what I do, please subscribe. Until next time, bye!